Good morning, everyone. So this is the third lecture of chapter 6. So as you know that chapter 6, we are dealing with truss analysis, the force analysis of truss system, right? So we covered two methods, method of joints and method of sections. So today we are going to do some more practice on method of sections. So you already have the handout. I uploaded the handout for today's lecture. So we have two problems on this handout. So we'll go and solve these problems on your handout. Okay, so on the screen you can see this is the first problem of your handout. So we have this truss with two supports at point A and point K. And then we have 1, 2, 3, and 4 external forces. And we have a number of members and what we need to find in this. If you go through the statement, determine the force in members CD, HI, and CH. So there's a typo in this third member. This is CH. So find the force in these members of the truss and state if the members are in tension or compression. Okay, so now this is the truss, and we need to find the member forces in CD. So let's see. This guy, CD, HI, and CH. So we need to find the forces in these three members. Now we know that we are doing the method of sections, but I mean, just in case, okay, if you have this problem and it's not given that which method you want to do. So if you want to go for method of joints, then you may have to start, let's say, from this point, right? So, or maybe this point, right? So that's the problem with method of joints. You cannot directly come in the middle of the truss and find out, like in this case, let's say forces and members HI, CH, and CD, right? So you have to solve maybe 3, 4 members before coming over to the middle of the truss. Okay, so method of section gives this flexibility to cut a section anywhere where we are interested in getting the forces in the members, right? Okay, so now this is the truss and we are using method of section. So first of all, let's write down that. Okay, so number one, we will use method of sections. It's also important to write down the statement because we need to tell that, okay, we are doing this method to solve this problem. Okay, now if you look at the truss, so where should we cut the section? So we know that we have to find these 3 member forces, so we should cut the truss like this, right? Let's say this is section AA. Okay, so that's how, by making this cut, we are cutting all the 3 members in which we require the member forces. Okay, so that's a good cut, which gives us these 3 member forces, right? Okay, so now we can go ahead and say that, okay, make a cut, say at section AA or A-A, right? So we are done with the cut. Now the next point or next step is to see which side of the cut we want to analyze, right? Now in this case, if you take the right side, okay, we don't have to find support reactions, so that's good. We have 3 external forces, okay, and then we can find these 3 member forces. Okay, so that's a good option. Now if you take the left side, you need to find these support reactions at point A and point K, right? So that's an additional step. if you take the left side, right? And you also have two external forces, right? Okay, so with that in mind, just by, visualizing the analysis of both the sides, so we'll say that, okay, right side is easier, okay? So that's why we want to go for the analysis of the right portion of the cut, right side of the cut, right? So once we decided that, okay, we are going to take the right side, so let's write that. Let's say consider right side of the cut section and do the force analysis. Okay, so consider the right side of the cut section and do the force analysis, right? Now, next thing, do we need the support reactions? Because we are taking the right side and the supports are on the left side, so we don't need the support reactions, right? So we can just write that. We do not need support reactions, or we do not need to find support reactions because we are considering the right side. Okay. Now, what's the next step? So to start the analysis of the right side, we should have a free body diagram of the right side, right? Okay, so make a free body diagram of the right portion. The truss. Okay, so if you want to make the free body diagram, let's make the free body diagram here. So we have this, and we have this. Okay. Okay, something like this. And we have a cut here, right? Okay. So let's. Okay, so this is your cut AA or A-A, and this is the right side of the cut section. Okay, now let's use some different color and show the member forces, right? So this guy is FHI. If you remember the rule, always take tension in all the members, right? So let's take, this is FCH, and this guy is FCD. Only if you can make out that there's a compression, then you can take compression, otherwise take tension in all the members, right? And in the end, if you get a positive number, then it means that it's a tension. If you get a negative number, then you can change the direction and you can say that it's not a tension, it's a compression force. Okay, so we are done with the free body diagram. We have applied these member forces, right? We have taken tension for all the members. Now just put the dimensions, or just put the, let's first put the external loads. So what are the external loads we have? We have these three, right? This is 1,500 pounds. This is also 1,500 pounds. This is also 1,500 pounds. So these two, this is D, this is H. Okay. And if you write down this, it's E, this is G, this is F. Okay. So now we got a free body diagram. We got the forces. We do not need the support reactions. Okay, so now we can just apply the equations of equilibrium and find out these unknown member forces, right? We have three equations of equilibrium and we have three unknown member forces. So this is determinate structure, right? Okay, so let's go to next step. And now to find out these three member forces, we can take moments, we can do sigma Fy, sigma Fx, we can use all these equations. But it's easier to take the moments at some point, right? So in this case, let's take moments at this point H, right? So because if we take moment of point H, then FHI is gone, FCH is gone. So the only unknown will be FCD, right? So let's do that. So take sigma MH equals to 0, right? So we need sign convention, counterclockwise positive, summation of moments at point H equals to 0. And once you do that, you get negative FCD times 4, negative 1,500 times 6, negative 1,500 times 3 equals to 0, right? So this FCD times 4, which is the moment arm between the force and the point where we are taking moment, point H, then this first 1,500 pound force at point D is passing through point H, so it's not giving any moment, right? And then the other two 1,500 pound force, they are creating the clockwise moment, so they are also negative, right? So all three are negative, and we got the moment equation, and from here we get FCD, which is negative 3,375 pounds. So we assume tension, but we got a negative number, which means that FCD is basically a compression force. So we'll write down 3,375 pounds and in the bracket compression. So that's how we are done with one unknown, right? Okay, so now we are left with two unknowns, FCH and FHI, right? So now we can take moment at this point, right? This is your point C, okay? Because if you take moment at point C, then FCD is gone, FCH is gone, and the only thing left is FHI, so you will be able to find FHI, right? Okay. So, sign convention, counterclockwise positive, summation of moments at point C equals to 0, right? So if you do that, we have only one unknown, FHI times 4, because it's creating a counterclockwise moment at point C. Then you have a clockwise moment from all the three external forces. So this is the moment equation for point C, and from here you get FHI equals to 6,570 pounds, right? And since we get a positive number and we assume tension, We'll say, okay, this is a tension force. Okay, so this is how we got our second unknown done. Now we are done with FCD, this guy. We are done with FHI, this guy. Now we are left with one unknown, which is FCH, right? So we are done. We are left with FCH. So we know that FCH has two components, right? It's an inclined force, so it has two components, X component and Y component, right? So we can just do sigma fx or sigma fy, and we can find out the value of FCH, right? So let's do sigma fy. So upward positive, let's do sigma fy equals to 0. And from here, what we get, negative FCH times 4 by 5. So this is the Y component, because we have this triangle ratio here, 3, 4, 5, 3, 4, and 5. Right? You can get this triangle ratio from the dimensions given for the truss, right? So that's how we got this triangle ratio, and this FCH is acting downwards because we assume tension. So negative FCH times 4 by 5 is the Y component, and then we have 1,500 newtons, 1,500 pound forces acting downwards. So negative 1,500 3 times equals to 0. From here, we get FCH as negative 5,625 pounds. So we assume tension, and the answer came out negative. So, which means that FCH is 5,625 pounds compression, right? Okay, so that's how we are done with this problem. Okay, we wanted to find 3 member forces, and this is how stepwise we did this problem. And now let's go to the second problem on your handout. What is the second problem? Okay, so problem 2 on your handout. Just draw this problem really quick. Okay, something like this. We have a roller support here. We have a pin support at point A. This is point B. This is C. This is D. This is E. This is F. Okay, so these are joints. Okay, and then we have some external forces. We have 4 kilonewtons force here. We have 8 kilonewtons force here. And then the dimensions you already have on your handout. I'm not going to draw the dimensions. Okay, so this is your truss. Now we need to find the member forces in which members. So requirement is FAF, BF, FBC. So member forces in these 3 members, right? So which members? Let's, AF is this guy, BF. Oh, I forgot to draw this member. Okay, so we have this member and this member, right? So we need member forces in these three members. Okay. All right, so let's go to the solution. How we are going to solve this flow. So step one, let's use method of sections, right? So using method of sections, okay. Now, you know that method of sections, we need to make a cut. Now we have these three unknown forces and these three members, AF, BF, and BC. So we can just make a cut like this, right? Let's say AA. Okay, so let's write that down here. Make a cut at section AA, right? Okay, and cut the cross into two parts. Okay, now next question is, do we analyze the top part or the bottom part? Now, if you look here, we have three support reactions, two support reactions at point A and one support reaction at point B, right? So if we take the bottom part, then we need to, find out the support reactions, unknown support reactions first. So we don't want to do that. So to ease our analysis, we'll take the top part, right? Because if you take the top part of the truss, then you do not need the support reactions, right? So let's do that. Take the top part of the cut section. Okay, so next thing, we do not need to find support reactions. Again, because we are analyzing the top portion, right? Okay. What next? Draw a free body diagram. Because we know that without free body diagram, we cannot do this, right? So draw the free body diagram of the top part. Okay, so let's draw the free body diagram. Okay. Okay, this is this, this is this, this is this. Okay, and this is your cut section AA, right? Okay, now again, let's assume the member forces, right? So let's assume tension in all the members. So this is your FBC, this is your FBF, and this is your FAF. So we have assumed tension in all the member forces, right? Okay. So we are done with the free body diagram. And we also have this 4 kilonewton force and 8 kilonewton force. Again, I'm not going to draw the dimensions. You already have the dimensions on your handouts. So now let's move forward. Okay, so now apply equations of equilibrium to find the unknowns. What are the unknowns? The unknowns are the 3 member forces, right? Because we are not determining the support reactions, we do not need that, right? Okay. So first thing, this is point C, this is point F, and this is point B, right? So if you look at the free body diagram, it's good to take the moment at point B, right? Because if we take moment at point B, FBC is gone, FBF is gone, and the only thing left is FAF, which is creating moment at point B, right? And also the 2 other external forces. So we can easily find FAF. Okay, so let's take moment, counterclockwise positive, summation of moments at point B equals to 0. If you do that, you get FAF times 1.5, which is the moment arm of this FAF. Then we have 8 kilonewtons force, so 8 times 2 is the moment arm, then -4 times 4 is the moment arm equals to 0, right? So we have these 3 forces creating moment at point B, right? And FAF is creating clockwise moment, so it's positive. Then the other 2 external forces, 4 kilonewtons and 8 kilonewtons, they are creating clockwise moment at point B, right? So these are negative, okay? So from this equation, you just get the value of FAF, which is 21.3 kilonewtons, and we assume tension, so it came out a positive number, so it is a tension force. Okay, so we are done with one unknown. Now we are left with 2 unknowns. So now let's see, we want to find FBF and FBC. Okay, so now if you look at this free body diagram, and if you want to take the moment at, let's say, point F, because if you take the moment at point F, then FAF is gone, FBF is gone, the only thing left is FBC, right? So we can just find out FBC from here, right? So let's take moment, counterclockwise positive, summation of moments at point F equals to 0, right? So if you do that, what do you get? It's negative FBC times 1.5, that's the only unknown force, and then 8 kilonewtons is also gone because this is also passing through point F, right? So only external force which is creating moment is 4 kilonewtons. Again, creating clockwise moment, so negative 4 times the moment arm is 2, right? Equals to 0. So from here, we get FBC equals to negative 5.3 kilonewtons. So as we assume tension, we got a negative number, so which means that FBC is 5.3 kilonewtons compression force. Okay, so we got FBC. Now we are done with two unknowns. The only thing left is FBF, right? So step number 9. Now, if you look at the free body diagram, we have FBC, we have FAF. The only thing we require is FBF, right? So FBF is inclined force, so it has X component and Y component both, right? So even if we do sigma Fx, we can find sigma the FBF. Or if we do sigma Fy, we can again find out FBF, right? And from the dimensions given, you can just make out that this triangle ratio is 5, 3, and 4, right? Okay. So just let's do sigma Fx equals 0. Right word positive, sigma Fx equals to 0. We have 4 kilonewton force positive, then we have 8 kilonewton force positive, and then we have FBF times 3 by 5. This guy, FBF times 3 by 5 means horizontal component acting rightward, so it will be a positive equals to 0. And from here, we get FBF equals negative 20 newtons. So now, if you remember, we assumed tension force here, right? FBF we took as tension force. It came back as a negative number, which means that FBF is not a tension force, it's a compression force, right? So you need to write this big C in brackets with the answer, right? And it's very important to write down this big C or big T to show that either it's a tension force or a compression force in your answers. Otherwise, we may lose points. So that's how we are done with this problem, applying method of sections on this truss and finding out these 3 member forces, right? So whenever you do this method of sections for the force analysis of truss systems, use these steps, because these steps will guide you through the process of using method of sections, right? And doing the force analysis correctly. Okay. All right. So that's all about today's lecture, and I will see you in the next lecture. Thank you.